all of Calc 2 in 30 minutes. Okay. Calc 1's all about derivatives, rates of change, defining them as limits of difference quotients, derivative rules, derivative applications, including to optimization and so forth. And then at the end of Calc 1, you get into integrals a little bit. In Calc 2, we start with a review of integrals from chapters 5 and 6, the beginnings of integrals. And I know what we focused on in here was thinking about physics examples, like if we got the velocity v as a function of time, maybe it looks like this over some interval from a to b. Let's go ahead and pretend, just for the sake of doing it, this is representing left-right motion instead of up-down motion. Left-right motion, when the velocity is positive, you're moving rightward, that's the positive direction. Sorry, left-handers. Okay, my son's a left-hander, so okay. Sorry, that's just the way we do things here. And then move in the other direction, the leftward direction, that's a negative velocity. So we're starting off with the positive velocity, moving to the right, getting close to zero, but not equal to zero until we get right there. That's the moment when we turn around and start heading to the left. And then we turn around and head back to the right at that moment in time. So this is a back and forth kind of motion. What are we interested in knowing? We're interested in knowing a couple things. Maybe the total distance traveled by integrating the absolute value of the velocity. Or if we want to ignore absolute values, the integral of the velocity gives you the change in position, not the distance traveled. Displacement. Since I'm thinking of it as back and forth motion, maybe I want to denote the position by the letter x instead of y. The position is a function of time, say, call it capital F of t, hint, 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 it will be an antiderivative of the velocity. And the basic principle about integrals in this context is that to find the change in position, you integrate the rate of change of the position, you integrate the velocity. Call this v equals little f of t. The change in position over this interval, which could also be written with the function notation as capital F of b minus capital F of a, is the integral of the velocity, little f of t, from a to b. And that will be, in terms of areas, if this area is A1, this area is A2, and this area is A3, for this picture at least, this equals A1 minus A2 plus A3. If I think of A1, A2, and A3 all being positive areas, I have to subtract the A2 because the graph is below the axis. But as far as rigorously saying what those areas are, we had to use limits. We could approximate the areas with areas of rectangles. We could approximate areas. If the function is nice and continuous, those Riemann sum areas will have a limit as delta x goes to 0, or as the number of rectangles goes to infinity. You can prove, it's a senior level kind of math major proof, that if your function is continuous, such a limit will exist, and in fact, even be consistent no matter how you construct your Riemann sums, whether you do left-hand rule, right-hand rule, midpoint rule, or even arbitrary sample points in each subinterval. It won't matter if the function's nice. So it's a very solid kind of concept in terms of defining the areas. But that doesn't tell you how to compute it. What tells you how to compute it is this equality right there, and that essentially is FTC part 1. Now, I didn't say that was a theorem here at first. I was describing it intuitively. To find the change in x, effectively, intuitively, add up. The integral is like adding the little changes. You could call these dx's. And you could even pretend that f of t dt is a multiplication. This is the infinitesimal approach. You could pretend, okay, dt is a tiny interval of time, maybe in seconds, and f of t is maybe a not so tiny velocity in meters per second. Multiply, pretend you're multiplying, and the seconds cancel, giving you meters. And dx would be a tiny distance traveled or a tiny displacement in meters. And the integral's like adding. That's an intuitive approach. It's not rigorous. But people like it. Scientists like it because they like having intuition about these things. They don't really care about proving it, right? They either don't care or they don't know how to prove this thing. And I'm not trying to denigrate them by saying that. That's just reality. They either don't care or they don't know how, or both. Okay? They're usually fine with thinking about this intuitively. Just realize that's what they're doing. They're saying this is true because it makes sense to them based on their experience over many years. And you want to get to the point where it makes intuitive sense to you, even if you don't care about proofs or don't remember how to do them. And we never actually prove this in here. To prove it involves technical things like limits of Riemann sums and there's a mean value theorem for integrals, and there's all sorts of things, theoretical things that can come together to help you prove this. For us, it's sort of beside the point being in a calculus class. But we're happy that it's true. Integrals, of course, all have all sorts of other properties. For example, linearity. We don't appreciate this property as much as we should. Just like with derivatives, the corresponding property of derivatives, this property is really essential. Linearity of the integral. There's also a property regarding limits of integration that looks like this. We don't appreciate this one as much as we should as well. This one's pretty handy, especially if your function f of x is a piecewise function, which it sometimes is, for example, in probability and statistics. We sometimes use piecewise functions for real-life applications in probability and statistics. The PDF, for example, might be a triangular distribution. Graph is a triangle, so it's best to represent it as a piecewise function. And if you're going to integrate it, you need to integrate over each piece individually and add the results. So there's those properties. Coming into chapter 6, there's also the second fundamental theorem of calculus, FTC2, that tells you how to differentiate an integral. Here's the way you can write it, or one way to write it. And realize this x needs to match this x, needs to match this x. But the variable that I use in here doesn't matter. Don't pick a, x, f, or d for that other variable, because those are already being used. Pick a t or a u or a w or maybe a Greek letter or something. Okay. Scientists will often get sloppy here and write x's there too. That's sloppy. We really should be precise and really emphasize what's truly varying is the upper limit of the integral. The purpose of FTC1 is to evaluate integrals. Got an integral? How do you find the answer? Do that, assuming you can find capital F. This is different. Got an integral with a variable upper limit. How do you differentiate it? That's what this answers. It's like the d dx and the integral kind of cancel, but you do need an x there, not a t. This is important because it helps you construct, theoretically at least, antiderivatives of functions, even when you don't know what the integral is, even when you don't know an antiderivative. Like Mathematica. What's the integral from 0 to x of cosine of t squared? What is it? It's that. Square root of pi over 2 Fresnel c of square root of 2 over pi x. Now you know. Okay. What is Fresnel c? That's just a function. You just never heard of it before. Somebody named Fresnel defined it this way, I guess. It can be plotted, by the way. You can define it to be your capital F of X here. I can copy and paste this here, and I can enter that. I can evaluate it at numbers. F of 0 is 0. F of 1 approximately is 0.904524. The decimal in there just gives me a numerical approximation. If I get rid of it, it's not so helpful. I could also do / capital N. I could plot it along with cosine of x squared even. What do we have here? The gold colored graph is cosine of x squared. The blue graph is this Fresnel function. The blue is the integral of the gold. The gold is the derivative of the blue. The gold tells you the slope of the blue. It's positive here and close to 1. Gets smaller, gets to be 0 right there, just like we got a 0 value right there. Becomes negative, so the derivative has a negative value. 0 slope right there, gold has a 0 value. There are many functions that don't have elementary formulas. This is one of them, and they are useful. And how is the computer computing this graph? It's doing a bunch of numerical integrations. That's how. FTC 1 and 2 are both theorems. They're both always true. FTC 1 is not always helpful, even though it's true. It's always true. It's just not always helpful because you can't always figure out what capital F is. That's why we have to do numerical integration in the first place, to approximate integrals when we can't use FTC 1, because we can't figure out F, capital F. FTC 2 is true because it tells you how to find antiderivatives abstractly, which leads to practical algorithms like numerical integration, like Simpson's rule, for example. From there, we went into chapter 7. You got all your integration techniques: substitution, integration by parts. You could say tables is another technique, though I probably won't test you on that. Sometimes trig identities are really helpful. That came up on the gateway. Cos squared x plus sine squared equals 1 is certainly very helpful. But also, cos squared x equals 1/2 plus 1/2 cos 2x, and sine squared x equals 1/2 minus 1/2 cos 2x are really helpful too. In fact, take multivariable calculus. We use these a lot when doing double and triple integrals, especially when we use polar coordinates, or its generalization to 3 dimensions called cylindrical coordinates. There's also spherical coordinates. Think about latitude and longitude on a globe. These things are really useful in multivariable calculus for doing integrals there. We also did trig substitution, where we had to use these identities sometimes, trig substitution. We also sometimes had to use this identity: sine of 2x is 2 sine x cos x. And that came up on exam 1 with the hard integral that took a while. And we also had partial fractions. And we did the simplest kinds of examples there. You can make plenty of partial fractions problems that are really hard. We try to keep ourselves to the simplest kind. Then we did the numerical integration. Because again, the FTC 1, while it's always true, it's not always helpful. Numerical integration. Left, right, and trapezoid rule were done in Calc 1 even. New in Calc 2 were midpoint rule and Simpson's rule. We did error analysis, which also led, for example, to our version of Simpson's rule, which is different than you find in many calculus books, as being a weighted average of the midpoint rule and trapezoid rule. The reason we did it this way was we saw through examples that typically the midpoint rule and trapezoid rules, errors had opposite signs. If the error was midpoint was positive, the error with trapezoid tended to be negative. And also the midpoint rules error was usually closer to 0, about twice as close as the trapezoid's error. And so we take a weighted average, effectively averaging 3 numbers, mid-n, mid-n, and trap-n, mid-n twice. So take 2 times mid-n, add trap-n, and divide by 3, a weighted average for our version of Simpson's rule as the best rule to use. You will see in other calc books, they use a different method for Simpson's rule that involves a summation effectively. But this is the way that we did it. And that's the way you would be tested on it if I test you on it. Also, there's that knowledge about the errors. For example, if you increase n by a factor of 10, the error in the left and right hand rules goes down by a factor of 10. Trap and mid goes down by a factor of 10 squared, 100. And Simpson's rule goes down by a factor of 10 to the 4th, 10,000. 10,000 times smaller error if you increase n by a factor of 10. At the end of chapter 7, we had improper integrals. And then chapter 8 got into applications of integration. Applications of integrals. Kind of all along the way, throughout the entire course, to a certain degree, we've done probability applications, probability and statistics, including about a week or so of actuarial science applications. That's something that I've put in our course that's not in as much depth in other Calc 2 classes. I mean, hardly any Calc 2 classes do actuarial science applications. Some do prob and stats. Our book has prob and stats in it, but not as much as we did. We did normal curves. We did exponential distributions. We did uniform. We did triangular distributions. With the normal curves and exponentials, we had to use improper integrals, right? You want the total area under your PDF to be 1. If it was a normal distribution, bell-shaped curve, it goes on forever. You've got to do an integral from minus infinity to infinity, which, to tell you the truth, for a normal distribution is impossible to do using calculus 1 or 2 techniques. You actually need to verify it using multivariable calculus. But we trusted that the idea of convergence still worked. With the exponential distribution, we could do it. We applied it to actuarial science. We were thinking about random variables using the CDF method. For what goal? To find the CDF of a transform random variable. Z is, for example, a present value of a future $1,000 payment. Assuming we knew the distribution of T, maybe exponential, maybe uniform, maybe triangular, we could figure out the distribution of Z. It's CDF, it's cumulative distribution function. It's PDF by differentiation. Then find the mean and the median using various techniques. Other applications that are more standard included area, volume, arc length, so geometry applications. Within that included parametric equations and polar equations. Also, with the volume, we considered volumes of revolution, solids of revolution. People typically find those difficult. It's especially difficult to draw, and maybe that's why people find them difficult, is because they're difficult to draw. With a volume of revolution, a solid of revolution, you slice it perpendicular to the axis that you're rotating it around. And the cross sections are either discs, circle and an inside of a circle, or ring shapes. You could call them washers. You could call them an annulus, is another word. the region between two circles. We also had some problems where we said the cross section is a equilateral triangle or a semicircle or a square. And you integrate that cross-sectional area function to find the volume. Arc length integrals always involve square roots. They were typically hard to do by hand, though we did do it on one exam with a parametric curve. And the integral wasn't terribly difficult to do. I made the example where it wasn't too terribly hard. But they can be tricky. We did with polar equations. Remember with polar equations that the area is an area swept out by the polar curve, r equals f of theta. This type of area in general. The hardest part about those was figuring out what the angles are. Sometimes you have to look at the polar equation. I think that's what came up on the exam. We also did finance applications, compound interest, annuities. We did talk about both continuous and discrete annuities. On exam 2, the problem was a continuous annuity that was leveled, meaning you were getting money every second of every day. And to find the present value and future value, you technically had to do an integral. Though many of you didn't do an integral, you assumed it was a discrete annuity and used geometric series. Yes, we did do some problems like that as well, but that's not what the exam question was about. It was a continuous annuity. You're getting money at a constant rate, effectively every second of every day. Like with Elon Musk, if he was giving you $1 billion a year at a constant rate, that converts to 30-something dollars every second. If it was $1 million, it'd be what? More like 3 cents every second or something. Okay. If it's less than that, then it's a fraction of a penny every second, but it's an abstraction that's still useful. Chapters 9 and 10 were sequences and series, including the very special series, geometric series, and other special series, power series, and Taylor series. A sequence was just a list of numbers given by a formula quite often. For example, 1 over n squared, which is an example of something that goes to 0 as n goes to infinity. That's just a sequence, an infinite list of numbers. No adding going on. We also talked about recursive sequences. But most important for us was series. An infinite series say a generic one like this, where you pretend you have the convenient fiction of pretending you're adding numbers forever. I mean, we have lots of convenient fictions in this class that also included the infinitesimals with applications of integrals. And I think on exam 2, with one question, when I said to derive the integral, I said you could do it either with the Riemann sum or the infinitesimal approach, and that would be consistent on the final exam as well. You can do it either way to derive what integral to compute. Here we're just pretending to add up infinitely many numbers, but we're pretending in a way that can be made rigorous and also turns out to be useful, even though it is just pretending. You define the corresponding sequence of partial sums. Sn is the sum k goes from 1 to n of ak, say. That's a1, a2 up through an. Just using a different index of summation here because I want to think of n as fixed when I use this. For a given infinite series, you can always define the sequence of partial sums. And the most important thing to realize here is that the series either converges or diverges based on whether the sequence of partial sums converges or diverges. It's completely determined by it. If the sequence of partial sums converges, if the limit as n goes to infinity of Sn exists and equals some number s, we say the infinite series converges to S, and we even write that it equals S, even though we haven't literally added up infinitely many things. We just pretended that we did. So we are treating the infinite series, in the case of convergence at least, as a number. Really, it's a limit of numbers, which of course, if the limit exists, is a number, but we're not, again, literally adding up infinitely many things. We are making our pretending rigorous this way, and it turns out to be useful. That also led to many kinds of convergence/divergence tests. Convergence/divergence tests. The most fundamental of which is the divergence test, something actually labeled with the word divergence test, that says if the ANs in the series don't converge to 0, there's no way the series converges. It definitely diverges. But let's think about a very special series here, a P series. Say with P positive, so that we are dividing by n to a positive power. P series, we know, converge if P is bigger than 1 and diverge if P is between 0 and 1, including 1, because it's the harmonic series. We proved this with the integral test, but realize that this one example is enough to encompass the fact that we need series tests. Because these ANs, if P is positive, do go to 0 as n goes to infinity, no matter what positive P you have, even if P is between 0 and 1. But that's not enough to guarantee convergence. You need tests. You need the integral test. You need the ratio test. You need the alternating series test sometimes. There are other tests that we skip. There's something called there's a comparison test. There's also a limit comparison test. There's also a root test that we didn't talk about at all. There are a bunch of tests for series convergence. Series convergence would be easy if you could figure out what the SNs are. But typically, you can't do that. Typically, it's impossible to figure out what SN is. And finally, we had power series, Taylor series, and the last chapter, differential equations, DiffEqs. Power series are infinite sums of powers of x, positive powers of x. They always have a radius of convergence and an interval of convergence. Taylor series are special power series where you've got a function and you want to figure out a way to represent it as a power series. They still have a radius of convergence and an interval of convergence. These things can be memorized. They can also be derived based on the definition of Taylor series or some other formula by substitution or differentiation or integration. And then differential equations. What are they? What does it mean to be a solution? Separation of variables, slope fields, numerical approximation with Euler's method, applications to growth, decay, logistic growth, predator-prey model, competing species. And we also did free fall with air resistance and without, and also mass on a spring here at the end.